Thanks everyone for joining in. So today I'll be presenting some of our work related to the impacts of hurricanes on biogeochemistry in the ocean. And my main collaborators in this um, research are Ruby from PNNL. And we also have Laura Baianucci, who was formerly at PNNL and now at Fisheries and Oceans Canada. Greg Foles from NOAA AOML, and Julia Moriarty from the University of Colorado Boulder. So tropical cyclones or hurricanes are the most destructive and persistent natural hazards in the global tropics and subtropics, including in the US. So to date, the deadliest natural disaster in the US has been a hurricane, which is the Great Galveston Hurricane of 1900. So it was basically a Category 4 hurricane that made landfall in Galveston Island near Texas and was responsible for nearly 10,000 fatalities. So that's that. And then when it comes to economic losses, again, the top 5 and 7 out of the top 10 costliest natural disasters in US history have been hurricanes. So basically, from a societal standpoint, hurricanes are very, very significant. So before we go further in this topic, I want to give you a brief overview of how hurricanes interact with ocean and some of the physical aspects of it, which are very important for us to understand the later part of today's talk. So hurricanes are essentially nature's idealized Carnot engines, and they actually intensify by extracting heat energy from the ocean surface. So when a hurricane is over the ocean, it induces tremendous vertical mixing, which leads to entrainment of cooler water from the subsurface to the surface, which leads to cooling of the sea surface. So this is illustrated in this schematic here. So this is a typical temperature profile in the tropics. So you have warm sea surface temperature at the surface, and then, so this is the mixed layer. And then you have a rapid decrease in temperature below it, which is the thermocline. And below that, you have the deep ocean. So this is a classic 2.5 layer ocean. So when you have a hurricane passing over it, you have violent mixing that happens. And because of this colder water from the thermocline and below the thermocline is entrained into the surface. So this results in cooling at the surface and also a little bit of warming below the surface in the thermocline. So this cooling acts as a negative feedback onto the storm's intensity, because the hurricane, as I mentioned earlier, intensifies primarily by extracting heat from the ocean surface. So it's very, very sensitive to changes to the sea surface temperature. So this is a self-induced negative feedback for the storm. So this sea surface cooling is a classic feature of hurricanes and can be observed from space. So this is an example of that. So this is Hurricane Katia from 2011. And what you can see, so this is from the microwave satellite. And you can see the track of the storm. And you see intense cooling on the right-hand side of the storm. So in the northern hemisphere, the cooling is asymmetric, and it is more stronger on the right-hand side, because the way the storm the winds of the storm are in resonance with inertial currents at the surface. So that is why on the right-hand side, there's stronger cooling. But anyway, the point is there is a strong sea surface cooling at the surface. Now, so how does this affect things when you look at synoptic timescales? So on one hand, because this cooling happens, the atmosphere has to work more and try to, and more work is done by the atmosphere to bring it back to the pre-storm state. So more work is expended by the atmosphere through surface fluxes. And also what this can do is to impact other storms, as can be shown here. So here you have the same track of Hurricane Katia, again from 2011, and you have the sea surface cooling. Now, this sea surface cooling has a time scale, restoration time scale of approximately a month, so it is quite persistent. So while the sea surface cooling is there, if another hurricane passes over it, then it can actually impact the intensity of the second storm negatively. And this is something that we have seen in the past and documented in some studies. So this is on synoptic timescales. And then some studies have also shown that hurricanes can also impact climate. So as we have seen earlier, so in this schematic, what we are seeing is, so you have the initial temperature profile, and then you have a hurricane passing over it, and then the mixing causes a cooling at the surface and warming in the subsurface. Now the atmosphere will restore the surface cooling back to the pre-storm state over a period of time, but then the warming in the subsurface below the in the thermocline remains. So this is a seasonal thermocline. And in steady state, you cannot have a buildup of heat in the tropics, so it is discharged towards the poles as oceanic poleward heat transport. Some studies have estimated this to be as much as 0.7 to 2 petawatts. So this is a significant fraction of the oceanic poleward heat transport in the tropics. And there's also some studies showing that tropical cyclones can or hurricanes can lead to permanent El Nino-like conditions during the early Pliocene. So the way this happens is, again, during this period, the early Pliocene, there was much more tropical cyclone or hurricane activity than what is observed in today's climate. And as we have seen, these tropical cyclones are capable of pumping heat down into the depths of the ocean. And so what this happens is, this heat can be transported in the Pacific, initially through the equatorial undercurrent, and then which is transported further eastward and surfaces in the eastern tropical Pacific. So this actually has been suggested as a mechanism for maintenance of permanent El Nino-like conditions during early Pliocene. So these are some of the ways in which hurricanes could even impact climate at longer time scales. So with this background, now we can go ahead into today's topics. So we have seen the physical aspects of hurricanes. The question is, can they actually play a role in the biogeochemistry of the ocean? And I will try to convince you that it can do that using two studies. One is looking at the role of hurricanes in chlorophyll blooms in the North Atlantic. This is an open ocean study. And then the second study, where we look at the impact of hurricanes on hypoxia in the northern Gulf of Mexico. The first study is a relatively simple and more straightforward study. So in the interest of time, I will only go over the main results from this. And I will spend more time on the second study, which is a bit more complex. So let us go to the first one. So the tropical ocean is very highly stratified. By that, again, let us look at a typical temperature profile in the tropics. So this is from the Eastern Tropical Pacific. These profiles have been extracted, I think, near the Costa Rica Dome. So you have a warm sea surface temperature and a sharp thermocline, and then goes to the deep ocean. So when we say that the ocean is highly stratified, we have a shallow mixed layer and a strong thermocline or pycnocline. And because of this, mixing is harder to happen in the tropics. So, and consistent with this, what you see is these waters, the tropics, tend to be nutrient limited or oligotrophic. So coinciding with this, what you see is there is very little nutrients at the surface, and then you have a strong increase of nutrients into as we go into the thermocline and below. So what this means is at the surface ocean, you have light from the sun that is available abundantly, but you don't have too many nutrients for photosynthesis to happen. So this is the reason why most of the tropical oceans are oligotrophic. And in the tropics, you don't have very strong mixing agents. So and many regions are even known as ocean deserts. So if you're away from major rivers like the Amazon or Mississippi, typically you don't have a source of nutrients in the surface. So in these situations, hurricanes can act as agents of mixing that can mix down to hundreds of meters below the surface and bring nutrients to the surface. And once these nutrients are brought to the euphotic waters, then photosynthesis can occur and you can actually see chlorophyll blooms. So evidence for this was presented in the past. So this is a study by Babin et al. In 2004. And these are some of the first observations of chlorophyll blooms in the tracks of hurricanes. So this is an illustration of that. So in this figure, you can see two hurricanes, Bonnie and Danielle, from 1998, the Atlantic 1998 hurricane season. And you can see this is the track of Bonnie, and this is sea surface cooling from satellites for Bonnie. And what you can see is a significant cooling occurs here of several degrees, again to the right-hand side of the storm. And then these are images from the CBIPS satellite of surface chlorophyll. And what you can see is consistent with this region of sea surface cooling, you have elevated concentrations of chlorophyll after the passage of the hurricane. So there were several examples like this presented in this study and also in other studies. So while these studies showed effect of hurricanes on chlorophyll blooms, mostly as individual storms, now the question is, do they have a cumulative effect, and is that significant? So to answer this, we performed an analysis in the western subtropical North Atlantic. So this is the domain of analysis for this analysis. This is the domain that we have chosen for this analysis, and this region is known as the Sargasso Sea. And this is again known as a oceanic desert with very little chlorophyll, as you can see from this figure. You don't have too much chlorophyll here. And in this subtropical region, you again have a strong seasonal thermocline and nutricline, and it is characterized again by a shallow mixed layer and low chlorophyll. The interesting thing is the reason why we have chosen this domain is for a couple of reasons. One is it is a low chlorophyll zone, and also it happens to be a region with some of the highest track densities of Atlantic hurricanes. So in this map, we show the climatology of Atlantic hurricane track density. As you can see, in this region, you have some of the highest track densities found in the Atlantic. So this makes it very appropriate to test our theory that hurricanes can have significant cumulative effects on chlorophyll. So to do this, we first looked at the impact on the upper ocean mixing induced by hurricanes. So to do that, we used the mixed-layer depth as a proxy for the depth of mixing induced by hurricanes. And we look, so these are, so what you are seeing in this figure is the composite mean time evolution of mixed-layer depth anomalies in the aftermath of hurricanes. So this is based on oceanic reanalysis, daily ocean reanalysis data from HICOM. And what you can see is on the day of the hurricane and immediately after that, within a day or two, there's a significant increase in mixed layer depth. So this is what you can see is, and there's an increase of 6 to 8 meters. Now, this is a value that is averaged over a 4 degree by 4 degree box centered over the storm. So considering that it is averaged over such a large region, this increase is very significant. And individually, if you look at isolated regions, the deepening could be much more. So you see there is a immediate increase in the mixed layer depth, and this increase persists for nearly 10 days after the passage of the storm. So this is quite significant deepening of the oceanic mixed layer. And what this means is the subsurface water is entrained into the surface. Now we know that this subsurface water is not only cooler, but it's also nutrient rich. Now, to further quantify this mixed layer depth, the effect of hurricanes on mixing and mixed layer depth, we looked at the correlation between the seasonal accumulated changes in mixed layer depth with the hurricane, an index of the hurricane, such as the accumulated cyclone energy. And what we can see is this increase in mixed layer depth represents approximately 12% of the total interannual variability of mixed layer depth. So hurricanes are responsible for nearly 12% of the total interannual variability of mixed layer depth in the Sargasso Sea, which is pretty significant. So to again understand the impact of this deepening of the mixed layer on chlorophyll, we looked at the relationship between accumulated cyclone energy, which is again a measure of the overall hurricane activity, which takes into account both the intensity of storms and also the duration of storms. So, and then this is very well correlated with chlorophyll concentration over the Sargasso Sea. Over the period of analysis, the correlation is approximately 0.44, which means that hurricanes can explain nearly 22% of the total interannual variability of surface chlorophyll in this region. Now, to put this into context, this represents about 70% of the effect of the North Atlantic Oscillation, or the NAO, which is well known to have significant impacts on chlorophyll in this region. So that explains, that underlines the significant role of hurricanes in chlorophyll in this region. Now, briefly to look at the implications of this, what this means is hurricanes can play an important role in global primary productivity, and their impact is comparable to some major climate phenomena such as the North Atlantic Oscillation and so on. What this means is Earth system models may need to have a good representation of hurricanes in order to better simulate carbon cycles, global carbon cycles. So this is important to note. And the other thing that can also happen is that some studies have even suggested that there could also be a feedback mechanism operating between chlorophyll and hurricanes. So to illustrate this, let's consider this figure from Gnanadesikhan et al. In 2010. So they performed two simulations with an Earth system model. In one, they turned off the chlorophyll effect, and in the other, they turned on the chlorophyll effect. So we know that chlorophyll is very good at arresting shortwave radiation and confines it within the upper few meters of the ocean. So because of that, in experiments with chlorophyll, you would have higher sea surface temperatures, and consequently, it can impact some of the large-scale parameters that impact hurricanes, such as wind shear and so on. So in this experiment and their analysis, they show that when you don't have chlorophyll in your numerical models, the hurricane tracks in the Northwestern Pacific are biased towards the equator, or in other words, you have fewer tracks going further north. So, so what they have shown is Earth system models that don't account for the effect of chlorophyll on the upper ocean sea surface temperatures can actually develop biases in hurricanes. So it could also a good representation of chlorophyll is also important and can feed back to hurricanes. So this is the first study. Like I said, I just want to do it very briefly because we can go to the second study, which is a bit more involved. So before we get into this, I could pause briefly and take any questions if there are any, or I could take all of them at the end of the second topic.
It might be easier to do all at the end of the second topic.
Okay, thanks. So in that case, let's go to the second topic, which is related to the impact of hurricanes on hypoxia in the northern Gulf of Mexico. Hypoxia is a state of low oxygen which develops in the bottom of the ocean. And this is a very, very persistent feature in the northern Gulf of Mexico in the continental shelf along the coast of Texas and Louisiana, as can be seen in this figure here. So this develops nearly every summer. This is a persistent feature, and it mainly results from several factors. One is the seasonal increase in stratification that happens every summer, and also the nutrient loading from the Mississippi Atchafalaya river system. And the prevailing hypothesis is that when hurricanes pass over these regions, the continental shelf regions in the northern Gulf of Mexico, they actually mix up the water column, and there is ventilation of these bottom waters, and this alleviates hypoxia temporarily. So the question is that all there is to this, or are any other processes happening that are previously neglected? And we believe that one such process has received less attention, which is related to how hurricanes impact the sediments which are buried at the bottom of the ocean. So in this analysis, we have used the following data sets. We used daily rainfall from TRIM, vertical ocean temperature and salinity profiles from HICOM. We also used weekly estimates of total suspended matter from satellites, and we obtained estimates of bottom DO levels from the World Ocean Database and MCH cruises in the northern Gulf of Mexico. And finally, we used simulations using the ROMS model to support our observational analysis. So let us begin by looking at what happens in the aftermath of hurricanes. So this is the figure on the left shows the track of Hurricane Rita during 2005. Rita was a very, very intense hurricane. And what you can see in color is the change in sediments from after the storm and before from the difference in surface sediment level after the storm minus before the storm. So what you can see is, so these contours here represent the bathymetry of, and the levels I believe are 200, 150. So as you go closer to the coast, there's a sudden decrease in water depth. And what you can see is over the shallow continental shelf region, there's substantial increase in sediment concentration in the water. Or in other words, a lot of sediments are suspended. So as we've seen earlier, hurricanes are very, very good at mixing up the upper ocean. So when they are over the deep ocean, the mixing is mostly in the upper ocean and it doesn't feel the bottom. But once the hurricane gets closer and closer and into the continental shelf, where the depths are as small as 50 to 100 meters, the mixing reaches the bottom and is able to resuspend sediments that have been buried there. So this is not just an isolated case of one hurricane, and this happens very, very often. And this can be seen when we look at the composite mean time evolution of TSM, or suspended matter, for all hurricanes. And so this is weekly data. So you have week -1, and this is the week of the hurricane, 1 week later, and 2 weeks later. So what you can see is, with respect to compared to the week before, the TSM starts increasing during the week of the hurricane, and it reaches a maximum 1 week later, and then again it starts decreasing. So the maximum sediments are suspended 1 week later, but there is also a significant increase during the week of the storm. So the question then is, we know that in this region, the Mississippi River plays a big role in nutrient loading in the water. So when you have an increase in sediments like this, so the question arises as to what is causing this. Is it because hurricanes are mixing up the water column and resuspending sediments, previously buried sediments, or is it because once the hurricane makes landfall, there is a lot of rainfall and flooding of the river, which actually enhances the nutrient loading in the river discharge? So the question is there a way to separate these two processes? So to do this, we perform some analysis using precipitation, and we use sea surface salinity. So let us look at this figure here. So the upper panel shows precipitation during late August and September of, again, 2005. And this lower panel shows salinity. So both these are approximately time series at this location near the mouth of the Mississippi River, near the head of passes. So you have first, this is the case of Hurricane Katrina. On August 29th, the hurricane just reaches the mouth of the Mississippi River, and coinciding with this, there's a big pulse of rainfall. There's a huge increase in rainfall, as we should expect. This was a Category 3 hurricane at this point. And consistent with this, you see a sudden freshening of the water, freshening of the ocean surface here. So this is very consistent with this pulse of rainfall. And then the fresh water at the surface is gradually being restored back to the pre-storm state. And then approximately 8 to 10 days later, you have a second freshening, a bigger pulse of freshening, and this time it prolongs for more days than this initial pulse. So this initial pulse or this initial freshening is due to the rainfall when the storm is passing over that location, and 8 to 10 days later, you have the flood from the river, which causes the second pulse in sea surface salinity. And this is again seen during the Hurricane Rita, approximately a month later. Sorry. So consistent with this increase in rainfall, you see a sudden decrease in salinity at the ocean surface. And then this freshening is again slowly being restored back to the pre-storm state. And then approximately a week later, you see another huge pulse of fresh water. So this double pulse of salinity can clearly be seen from these two hurricanes, and it suggests that um, the influx of river is um, approximately occurs a week to 10 days after the initial passage of the storm. So using this, we can say that if there is an increase in sediments within 1 week of the storm, it is mostly due to local resuspension due to vertical mixing reaching the bottom of the ocean. And the increase in sediments in the second week or 1 week later after the passage of the storm is more likely due to the river discharge. And this is not just for these two storms. Again, the same thing is seen when you look at a composite mean, and this double pulse of salinity is a characteristic feature that happens here after almost every hurricane. And we have also verified this response using gauge data from USGS hydrographs at Bell Chase and Tabard Landing, again suggesting that the flooding of the river happens approximately a week later. So this is nice because this then allows us to separate these two effects on sediments. So with this knowledge, we can now start looking at the DO at the bottom of the ocean in the northern Gulf of Mexico. So what we are seeing on the left-hand side, the figure here is the probability distribution of hypoxia. And this is for 3 different periods. This is the pre-storm period, which is 1 week to 2 weeks before the storm. And this is the immediate post-storm period, which is 0 to 5 days after the storm. And then this is 5 to 15 days after the storm. So you have a probability of approximately 10 to 15% chance of finding hypoxia before the approach of the storm. And once the storm approaches, and then you have vertical mixing and there's ventilation of the bottom waters, hypoxia diminishes considerably, as you can see here. I mean, it's not completely gone, but it is reduced significantly. And then again, when you look at this second post-storm period of 5 to 15 days, hypoxia increases back to the pre-storm state, and sometimes it could even exceed the pre-storm state slightly because there's more nutrient loading from the Mississippi River. So what this means is now the period of interest for us is this initial post-storm period of 0 to 5 days. So this is immediately after the storm, before the discharge from the river, the flood from the river arrives. So now let us focus on this period for the rest of the analysis. So let us look at, to understand the effect of hurricanes on bottom DO, we take advantage of the relationship between bottom DO and stratification. So here in this figure on right hand side, what you can see is in black circles, this is the scatter between bottom DO and the stratification, which is the change in density from the surface to the bottom of the ocean. And so this is in black circles, you have the pre-storm scatter, and in light gray, you have the post-storm or the immediately after the storm period, 0 to 5 day period after the storm. And then these are the two regression lines for these two data sets. And what you can see is compared to the pre-storm regression, the slope of the regression line is much steeper for the post-storm data compared to the pre-storm data. In other words, for the same change in stratification, you get a bigger change in DO for the post-storm state compared to the pre-storm state. And this is reflected again in the slopes of these two equations. So what you can see is, so this is the slope of the equation for the pre-storm state, and this is for the post-storm state. And compared to the pre-storm, the slope nearly doubles in the post-storm state. So what this means is there's more drawdown of DO for the same change in stratification, and this is due to the additional effect of sediments that have been resuspended in the water column. To understand this better, you can break this into what we believe is a two-stage process. So we believe that there is a two-stage process occurring here. So initially, so you start from here, So this is the pre-storm stratification that is typically observed in the northern Gulf of Mexico. Now, the first stage is when the storm arrives and there is immediate ventilation of the bottom layer due to mixing. And this is a near instantaneous process. So because of that, I think this is a safe assumption that mixing is almost instantaneous. And we can verify that using the temperature and salinity profiles. So you start with a stratification here, and then you go to near zero stratification, and you can follow the trajectory of the pre-storm regression equation. So you're going from here to a zero dz of close to zero. And if ventilation was the only process happening in the immediate aftermath of the storm, this is the DO you should expect in the period immediately after the storm. However, the DO that we expect is that we actually find is lower than this, and this is the DO that is actually observed in the profiles. So this difference between the DO that we should expect based on this regression line and the DO that we find based on the post-storm stratification is due to, we believe, is because of the additional drawdown of DO due to resuspended sediments, which remineralize and consume oxygen. And there's also some effect of restratification of the ocean. So these two processes act together and then reduce the DO in the water column. So what you finally see in the post-storm period is a combined effect of these two. And ultimately what we see is it depends on the relative strengths of these two processes. So using the mean values of stratification that we observed for the pre-storm and post-storm conditions and applying them to these regression equations, what we have estimated is that the effect of sediment resuspension and remineralization is approximately, it can be as high as 20% of the effect of ventilation. What that means is this process of sediment resuspension can be as much as 1/5 of this effect of ventilation. So this is based on observations. So note that we don't have, as you can see here, as many observations for the post-storm state compared to the pre-storm state. However, we have verified that these results are statistically significant. But despite this, we would like to verify these results based on observations using numerical models to offer more support to this theory. And to do that, we performed experiments using the ROMS model, and we used the case of Hurricane Humberto from 2007. So this figure on the left-hand side, top figure on the left-hand side shows the track of Hurricane Humberto from 2007, and this region is the location where we performed our analysis for this hurricane. So we performed two experiments with the ROMS model. In one case, we turned on the effect of sediment resuspension, which is a control case, and we performed a test case where we turned off resuspension. And so this is the effect. So in this figure, you can see the effect on the particulate organic carbon. And as we should expect, compared in the case with no resuspension, there's no increase of POC in the water column. But on the other hand, in the case with resuspension, do you have a significant increase in POC when the storm arrives? And consistent with this, here you see the effect on DO. And again, in the case without resuspension, you see a significant increase in DO after the storm. So this is a pre-storm, and then this vertical line indicates the arrival of the storm. So relative to the pre-storm state, there is an increase in DO in the post-storm. But when you have resuspension, sediment resuspension turned on, you can see this black line is below the pink or the magenta line, suggesting that the DO increase is not as much as what we should expect when you don't have sediment resuspension. So these numerical experiments further confirm the results based on observations that sediment resuspension is an important process, and it could actually lead to significant changes in DO after the storm. So the implications of this study are pretty important to note. So we see that in this analysis that I presented, we looked at the case of hurricanes which made landfall near the mouth of the Mississippi River. And as we saw, so there is an initial increase in sediments due to local resuspension, and later on you have further increase in sediments coming from the flood of the river. However, note that these major river systems like Mississippi only occupy roughly 15% of the global continental shelf regions. On the other hand, this resuspension of sediments occurs everywhere and is a ubiquitous process. And this can be seen here using, if you can look at this figure. So here we show the track of Hurricane Jeanne from 2004. And what we see is the resuspension of sediments in the aftermath of this storm. And so what you can see is there's a significant increase in sediments along the west coast of Florida and all along the east coast of uh, the US East Coast, including Florida and the Carolinas. And we know that there are not any major rivers here, unlike the northern Gulf of Mexico, where you have the Mississippi River. So this is showing that this sediment resuspension process can happen in regions even without major river systems. So what this is telling us is that Earth system models need to account for this process of sediment resuspension to more accurately represent the carbon and oxygen cycles in the models. And the other thing is, it also has implications related to climate change. Um, as we probably know that hurricanes, and a lot of studies are suggesting that hurricanes will likely become more intense due to climate change. And when you have more intense hurricanes making landfall and arriving at the continental shelf, you would expect them to resuspend more and more sediments. And because of this, there should be more drawdown of DO from the water column. However, one may also argue that along the same lines, ventilation could also increase. But note that ventilation is not just related to the vertical mixing of the hurricane, it also is dependent on solubility of oxygen in the water. So which actually would change when you have more warmer water. You would have less oxygen solubility in warmer waters in future. So what ultimately happens in the aftermath of hurricanes in future is a very, very complicated interplay of all these processes. So I think more studies are needed and further experiments and analysis are needed to try and understand what would likely happen in future, because hypoxia not only is of academic interest, it also has a lot of uh, important implications for fisheries and other commercial um, purposes. So this is the basically the summary of the two main studies that I wanted to present today, and hopefully I was able to convince you that hurricanes can significantly impact biogeochemistry in the ocean. And most of the material I presented today is based on these two studies that we have published. And thanks for listening, and I'll be happy to take any questions.